Welcome back. We're going to move from talking about the concept to actually using a specific example and seeing how this works. So what I've put up here is we have volumes of solids of revolutions part 2. That's today's lesson. So the equation we have two versions of it. Notice that they look identical except there's x's here and there's y's there. Usually in textbook this will say CD, but those are just your limits of integration. So let me start by saying what are we seeing in the formula, and then let's see how it applies to a problem. And I'll probably have to erase and move stuff, but we'll deal with that in a minute. All right, so what's in here? Let's focus on this one here. The total volume is pi times the integral. Now, remember, I've tried to communicate that this actually drives the whole integral. That's very important because that is a dx. This is your low x value, like along the x-axis, and this is your high x value. This will be the radius as a function of x. That means it's going to be written as x stuff and numbers. And this, the dx, is the thickness. The thickness of what? Of a disk. Why is it a disk? This is the volume of a cylinder, pi r squared h. This is the volume of a cylinder. There's just an infinite number of them. And when you add up an infinite number of things, that's an integral. So now this one, see it's a dy. That's in control of the integral. That tells you this is your low y value, and this is your high y value. So in a dx problem, you're going to be looking at the x-axis for your limits of integration. For a dy problem, you're going to look at your y-axis for your limits of integration. And this is going to be the radius as a function, or in terms of y, as a function of y. Okay, so that's what's in there. Let's do an example. Now, when you're doing these, in most of the sometimes you'll be given a picture, but you got to, draw the picture usually. I think I said usually twice. So this has bounded by. So we need to draw a region that has these boundaries. So let's do that. Here's my y-axis and my x-axis. And the square root of x looks like this. There's one boundary. Y equals 0 is the x-axis. There's another boundary. And x equals 4 is a vertical line. There's a third boundary. So the region in question is this region right here. This is 4 on the x-axis. It's this region right here. So previously we found the area of something like that. What we're going to do is we're going to revolve this. Imagine it's like, imagine you have the ground and there's a pole sticking out of the ground and the pole can spin, and let's say there's a little metal flag on it and you just go up and hit it and it would spin around like that. We're going to spin this around the central axis. If I were to take this and spin it around the axis, it would look in 2 dimensions like a reflection right here. To give it a 3-dimensional look, you take this edge here and you draw an ellipse. So it'll make a bullet shape. See, this is revolving around the x-axis, and it creates a solid that looks like that. Now, I'm going to include some videos. They're short, so you can see these animated on a computer. I didn't do them, but they're kind of nice to see so you can visualize what I'm talking about here. Now, what we're going to do to find the volume of that solid, that's what we're trying to do, is we have to cut this into slices. We're actually going to cut an infinite number of slices up, but we're only going to draw one so we can focus on it. Now, each slice is going to be perpendicular to the axis of symmetry. See the axis? See how it's symmetric about the x-axis? See how it's rotated about this horizontal line? So when I cut a slice, it's going to be vertical. So I'm going to draw an ellipse parallel to that base right there. That's one slice. And I'm going to exaggerate that thickness right there. So we can see that is one slice out of the whole solid. So what I want to do is I want to use that to figure out what's the radius and all that business. Now, first of all, how would you measure how thick that is? If I had a ruler, would I put the ruler, see how I'd put the ruler this way? I'd put it along the x-axis. If I mark this x-axis off, I could measure how thick that was. That makes that a dx thickness because I would put the ruler along the x-axis. And here is the radius right there, the radius. Notice how the radius goes from the axis up to the curve. The curve defines the radius. The radius begins at 0 and goes up to the square root of x. Why? Look, if it's at 1, it would go up to 1, because at 1, that would be the point 1, 1. At 4, it goes up to the 2. That would be 4, 2. What am I saying? The radius would be 2 units when x equals 4, right? I'm using this equation. If x is 4, the square root of 4 is 2. The radius is the function. That is vital. You have to get that to do these problems. Now, you're going to want to go a little bit too far with that. Later on, we're going to see you can't make it that simple. But for this first simple example, the radius begins at 0 and goes to the curve. So the radius is the curve. Now here, let's set up our equation. You have to look at this picture. If you start just say, oh, okay, I'm just going to put this in that slot. When we start getting more complex problems, you're going to totally mess this up. The picture rules these integrals. If you don't draw the picture, you're going to get them wrong. Maybe not the easy ones, but the minute we start cranking it up a little bit, you will get them wrong without the picture. Okay, this is non-optional. You've got to learn how to navigate the picture. So here's my equation, here's my picture, and I'm focused on that disk. The volume of this solid is pi times the integral from low, okay, look at it. Along the x-axis, this starts at 0, and it goes up to 4. See, that was the boundary at the 4. The radius, see it? It goes up to that curve, and this is the equation of that curve. So I'm going to use the radius, square root x squared, and the thickness is a dx thickness. That's it. Right there, it's either going to be dx or dy. It's dx if you would measure it like this with the ruler on the x-axis. It'll be dy if you'd measure it the other way. You're going to see that in a minute. See, there's the setup. All I got to do then is put that in my calculator and I've got it. See, getting the number answer is the simplest part. The hard part, the part you have to know how to interpret things for, is how do you set up the integral. It is pi, low x, high x. The radius goes from 0 to the curve, so I put the curve there, squared, and the thickness is dx. So now all I got to do is get my calculator, which I don't have on me, but I did already calculate this. Hopefully I have the correct number here. And for this one, I'm out of space. I'm going to erase right here. 25.13, and that would be units cubed when I plug that in the calculator. Now we're going to do this one. I'm actually going to erase all this stuff so I have a little more space here. Step 1, draw it. So see the boundaries? Let's draw those. Oh, I'd have to also say, I'd have to give you a domain restriction. X has to be greater than or equal to 0. All right. X-axis, y-axis. Y equals x squared. That should actually hit the origin there. Right? Except I'm limiting it to positive x's. So I'm going to get rid of this. There's boundary number 1. X equals 0. That is the y-axis. That's boundary number 2. And y equals 8 is a horizontal line up here at the 8. That is boundary number 3. And that creates a two-dimensional bounded region. And we're going to rotate that about the y-axis. So I'm going to spin it this way. And the way you draw that is you reflect this, and then you draw an ellipse right here to get the 3D effect. So this will be another bullet shape, but now it's vertically oriented, right? It looks different than it's the same shape, oriented differently. Okay, well, I could just start punching stuff in here, right? Who cares what the picture looks like? See these? These go in there somehow. Just put them in there. You're asking for trouble. Let's draw it. What do I mean by draw it? Let's draw one slice, because that's what this is, adding up slices. So let's see one. See the axis of symmetry? Slice it perpendicular. So I would slice it this way. What would that look like? It would look something like this, and it would have a certain thickness. Now look at that thickness compared to the last example. I would have to put my ruler this way to measure how thick that is. Or in other words, I would look at the numbers on the y-axis to figure out how thick that is. That is a dy thickness. And the radius goes from 0 to the curve. See how it goes to the curve? Which curve? This curve. So there it is. Here's my equation. Let's start punching stuff in. So the volume of this solid should be, we'll get these in a sec. Oh, I forgot. Volume is pi times the integral of the, now this is going to be wrong, but I'm going to write it because people do this. They write, okay, here's the function. See how it goes to that curve? So there's x squared squared, see, radius, the function squared, times a dy thickness. Well, this is a dy integral. You can't have x stuff in a dy integral. So what you got to do is you got to take this y equals x squared, and you got to solve it the other way. So x is the square root of y, right? So this is not acceptable. You have to put that in there. We've got to solve it for the other variable. Now, this is a dy, so I look at my y-axis, 0, up to, remember we went up to y equals 8. So that would be that setup. If you just start picking these out and throw them in there, I'm telling you, you're going to have trouble. If you don't believe me, you'll discover it on your own once we start doing them. You want to draw it, and you want to draw the slice, and you want to reason out if it's a dy or a dx. You want to visually see the radius, especially when we start rotating these about something other than the x or y axis. And then when we construct our equation, it's a lot easier. So now, this is the hard part. The easy part should be to just put that in our calculator. I already did that, and if I punched it in right, I got 100.53 units cubed, and it'd be cubed because it's a volume problem. All right, we're going to knock out one more example, and then I'll let you play with these. Just pausing a second. All right, example 3. Suppose it's bounded by y equals sine of x, y equals 0, x equals 2 pi over 3, and we rotate it or revolve it about Let's do the x-axis again. So these are our boundaries, and this is what we're revolving it about. Step 1, draw it. Sine wave looks like this. Y equals 0 here. Sine wave looks like this. Y equals 0 is the x-axis. And x equals, remember, this would be pi. This is pi over 2. So 2 pi over 3 is between there. 2 pi over 3. And that is a vertical line. So here's my region right here. That is the only region that has 1, 2, 3 boundaries. Oh, my bad. I guess it could be this one too. I want that one. I'd have to give you I want that one. I'm going to erase these. This is the region in question. If this were a test problem, I'd have to put a domain restriction so you knew it was the left side. But let's just get the concept down. There's my picture. Step 1, draw the bounded region. Step 1, draw the bounded region. And step 2, revolve it about the stated axis of rotation. So this is the x-axis. We're going to spin it this way. How do I draw it? Well, reflect this about the axis. And then here at the end, instead of drawing it straight down, draw an ellipse to give it that 3D look. So it looks like, a strawberry or something with the top cut off. Now what we have to do is we have to slice this thing up. If this were a strawberry, we're going to cut it up and we're going to do it perpendicular to the axis of symmetry. So one slice would look like this. I'm going to draw an ellipse. And then I'll put a parallel version right there so I can see the thickness. See the thickness right here? That thickness is measured along the x-axis. That is a dx thickness. And the radius is right here. And it goes from 0 up to the curve. Which curve? This curve. That curve right there defines the radius right here. We're ready to put it into the equation. The volume is pi times the integral from, what kind of integral is it? Square 1 is the thickness. It's a dx. So this will be my low x, 0, to my high x, which is 2 pi over 3, times the radius, which goes from here up to that curve, times the radius squared, times the thickness of that, which is a dx thickness. There's my setup. That is my setup equation. All you got to do is punch that in your calculator. When I did it, I got 3.97 units cubed. Okay, I want you to try the problems that I gave you to try. Be sure you work through them. Email me questions.